Hi, I'm Craig Putnam, one of the robotics engineering faculty here at WPI. And in this video, we're going to continue our exploration of operational amplifiers, or op-amps. Just as a reminder, in the last video, we looked at the ideal op-amp model and made some refinements to it, and then we looked at how to use an op-amp in the open loop configuration. In that configuration, remember, if you have just a very tiny difference, maybe only microvolts difference between the voltages of the inputs, the output will be driven to one of the rail voltages. The op-amp will be in saturation. So that greatly limits the ways that you can use the op-amp. So it kind of begs the question, what if we could reduce that gain? Could we then have more flexibility in how we use the op-amp? As we see here, this operational amplifier is in the open loop configuration. To reduce our overall gain of the circuit, we're going to use what's called negative feedback. In other words, we're going to send some known fraction of the output voltage back into the inverting input. We can accomplish this using the following circuit. Because we have created a loop in the circuit from the output back to one of the inputs through the resistor labeled R sub F for feedback, this is called a closed loop circuit. We are feeding back some of the output voltage into the inverting input terminal. We'll add an input resistor, R sub in, as shown, and finally we'll also connect the non-inverting input to a common ground reference. Notice that we now have only one voltage input to this circuit, which is labeled V sub in. An op-amp connected in this fashion is said to be in an inverting configuration. If your intuition tells you that making all of these changes to the circuit will alter its behavior, you're correct. Specifically, the overall gain of the circuit, which is defined as the ratio of the output voltage, V out, to the input voltage, V sub in, is given by the following formula. Another way of thinking about it is to say that the output voltage is equal to the input voltage times this gain. As you can see, the output voltage is opposite in sign to the input voltage. Hence, we use the word inverting to describe the circuit. So a positive input voltage will result in a negative output voltage and vice versa. In a later video, we'll show you exactly how this equation is derived. The most important takeaway, though, is that you can exactly control the overall gain of this circuit by simply selecting appropriate values for the resistors R sub F and R sub in. For example, if you wanted a gain of negative 12, you could choose the following resistor values. R sub F equals 12 k ohms and R sub in equals 1 k ohm. The gain would be minus 12, and if your input voltage V sub in was, for example, 1/2 volt, then the output voltage V sub out would be minus 6 volts. Note that the op-amp will still saturate at the rail voltages, so you'll have to pay attention to properly choosing the power supply voltages V++ and V-. Okay, that's great, but suppose we don't want a negative gain value. Is there a way to set up an op-amp circuit such that we get an overall positive gain? Well, the answer is yes, and this is the circuit that accomplishes that result. It looks pretty similar to the circuit we just looked at. It too is a closed loop circuit with a feedback resistor R sub F going from the output back to the inverting input. The major difference here is how the input voltage and the second resistor are connected. The other major difference is that we have a different formula for the overall gain. In this case, it is given by the formula gain equals V out over V in, that's the same, and that equals 1 plus R sub F over R sub in. Note that the gain in this case will always be a positive value. Thus, this is called the non-inverting configuration. As before, note that the output voltage will still be limited by the rail voltages. And again, we'll defer to a later video the process of actually deriving this equation. Before going on, let's recap what we've just seen. We now have two additional ways of configuring an op-amp to allow us to produce a smaller, more controlled gain value. We have a circuit that produces negative gain, and we have another circuit that will produce a positive gain. The absolute value of the gain for the inverting circuit can be greater than or less than 1. For the non-inverting circuit, however, the gain will always be a value that's 1 or greater. Now this begs a question. Can the gain of that non-inverting circuit be exactly 1 if we wanted it? And then it begs the further question, why would we ever want a circuit with a gain of exactly 1? I mean, what possible use could you have for a circuit where the output is exactly the same as the input? Well, the answer to that is that you can indeed build such a circuit, and we call it a unitary gain buffer, or sometimes it's also called a voltage follower. And this is what that circuit looks like. As you can see, it's a special case of the non-inverting configuration where the value of R sub F is 0, or a short circuit, and the value of R sub in is infinity, or an open circuit. Mathematically, both of these values drive the second term of the non-inverting circuit's gain equation towards 0. Okay, but that still leaves open the question of why and what would you use such a circuit for? To answer those questions, we need to go back and review a little bit about what we know about voltage dividers. We know that the voltage divider looks like the following. The voltage labeled V signal is given by this equation. We can model many sensors that output a voltage as behaving much like a voltage divider, where one of the resistors, R1 or R2, varies in proportion to something being sensed. That could be light intensity or temperature, force, etc. But we need to measure the voltage V signal in order to do anything with it, and in doing so we must add some additional circuitry. Let's model that circuitry as a resistive load R sub L. It should be apparent that unless R sub L is very large as compared to R2, the presence of R sub L will alter the value of V signal. In other words, if R sub L isn't a large enough value, it is said to load down the output of the voltage divider. Okay, so here's where we can use the unitary gain buffer. We haven't talked about this yet, but one part of the more complete model of an op-amp is that the input to the unitary gain buffer circuit itself behaves like a very large resistor. So if we insert a unitary gain buffer into our sensing circuit, we get the following. Because the unitary buffer has a very large input resistance, it does not load down the output of the voltage divider. Actually, impedance and not resistance is the correct terminology, but we'll get to that later. Thus, the voltage going into the unitary gain buffer is essentially unchanged. And because its gain is exactly 1, the output voltage is the same as the input voltage, V signal. Now, all of this would be for naught except for another property of the more complete model of an op-amp that we haven't discussed yet, and that is that the output voltage of the op-amp is independent of its load. Remember, the equation that we have for the behavior of the op-amp doesn't involve any load resistor on the output side. It doesn't show up in that equation. So that output voltage is independent of that. In other words, you can put whatever load you want on the output of the op-amp, and theoretically, in the ideal model, it will always produce the correct voltage across that load. So voila, we have now what we needed, which was a really useful circuit in order to make sure that we don't load down the output of a voltage divider type of sensor. Okay? So we can use this unitary gain buffer in this context very effectively. We can insert that between a sensitive voltage output device and the circuitry that's necessary to measure that and not load down the output of the device. So we've seen now some circuits that utilize op-amps in the both open loop and closed loop kinds of configurations. In the next video, we're going to get a bit deeper into the behavior of the ideal op-amp model, and we're going to get to the equations, how we derived the equations that we saw in this video. Be aware, in order to do that, you're going to need to be comfortable with Kirchhoff's laws and Ohm's law.